Welcome back, everybody. My name is Calvin Lin, and today we'll be going over random forests. A random forest is a prediction method that combines many simple decision trees, and it basically lets them vote. Each train is trained on a slightly different random sample of the rows, known as bootstrapping, and at each split, it only considers a random subset of the columns, which are called features. This randomness makes the trees less alike, so when their votes are averaged, overfitting drops and accuracy usually improves compared to a single tree. To use it, you pick your input columns, convert text categories to numbers, that's called OneHotEncoding, split into train and test, and we fit the model. The main knobs you'll see are how many trees to build, called N estimators, how deep each tree can grow, or its max depth, how big a leaf must be, or min samples leaf, and how many features a split can consider, max features. Forests work well out of the box on tabular data, handle nonlinear rules and interactions, and can report which features matter most. But they're slower and less interpretable than a single tree, and predicted probabilities may need calibration if you need precise scores. Today we're going to be training a random forest to predict who survives the Titanic using the famous Titanic dataset. We'll keep it simple. We'll just load the seaborn dataset, set up a pipeline that handles the missing values and categorical variables. We'll train the model, evaluate it with precision, recall, and a confusion matrix. We'll also take a look at feature importance. We'll also try a tiny tune-up, and yeah, let's get started. First, we're going to be starting with our imports. So these first three, NumPy, Pandas, and Matplotlib, are core libraries for numbers, tables, and plotting. This import right here is for model selection, that being the train test split, and just simple tuning. We'll import the accuracy score for overall fraction correct, precision recall, F-score support for precision recall in F1. We'll also bring in the confusion matrix to see raw counts by class. We'll also plot the confusion matrix to make it easier to visualize. And we'll also have a per class summary metric. This import right here is the specific model that we'll be training. This will allow us to do one-hot encoding. This will allow us to do imputing. This will not allow us to do simple imputing. We'll bring in ColumnTransformer so we can apply different transforms to categorical versus numerical values. We'll bring in pipeline for the chain preprocessing and the model. And we'll bring in a simple imputer so we can replace values that we need to. And we'll import a simple imputer to fill in any missing values. We'll get our Titanic dataset directly from Seaborn. These are just the Matplotlib defaults, and this will ensure that this notebook will have reproducibility. Let's import the model. We'll import the Titanic dataset from Seaborn, and we'll put it into a data frame. Taking a look at the Titanic dataset, we see that we have 15 columns, we have 15 columns with 809 rows. The next step is to pick a small, sensible set of features. In this scenario, we'll choose ticket class, the sex, age, family counts, fare, and the embarking port. In this scenario, we're interested in predicting whether or not, given a set of features, whether or not it is likely to survive or not. So that will be our target. And we'll have this in a survived column. We can see in our data set that approximately 62% of the data set died in the Titanic crash, while only 38% survived the Titanic crash. We also see that these columns mix numbers and strings, and if you recall from before, we have a number of missing variables. To handle this, we'll handle all pre-processing within the pipeline so the process is reproducible for later. The next step is to split the data into training and test sets. Around a test size of 0.25, as we've set right here, keeps 25% of rows for final honest evaluation. We set stratify to y, which preserves the original binary survival ratio in both splits. Let's take a look at how many rows end up in the train set and the test set. We have 668 rows in the train set, and we have 223 in the test set. Let's build the pre-processing and random forest pipeline now. Before we jump into building, it's important to go over two important definitions. Imputing fills in missing values, so the model sees it as a complete table. For numbers like age and fair, we will stick with using the median, which is robust to outliers. And for categories like embarked, we also will use the most frequent value. OneHot encoding converts text categories into numeric binary indicator columns. So if we take a look at sex, we'll turn it into sex female and sex male. This avoids pretending categories have an order, and it lets the model use them correctly. The first step is to tell the pipeline which columns are categorical versus numeric. We'll impute or encode them differently. So these two columns right here are categorical, and these 5 columns here are numeric. The next step in the pipeline is to define how to transform each type. For categoricals, we're going to fill missing values with the most frequent category. And then we'll one-hot encode to turn text categories into numeric columns. For the numeric columns, we're going to fill in missing values with the median. As we mentioned, it's robust to outliers. Next, we'll combine both transformers, so each applies only to its own columns. Any columns that are not listed are dropped. Now, let's define the model. 400 trees is a stable default for small to medium datasets. Setting max depth to none will let trees grow until pure, meaning the ensemble averaging reduces overfitting. Setting max features here will introduce randomness at each split, decorrelating the trees. Setting min samples leaf to 1 will keep leaves small, and we can tune this later if needed. Setting the njobs parameter to -1 will use all CPU cores. We'll bundle all of this into one pipeline, so the preprocessing and the model always move together. Bundling preprocessing and the model into one pipeline guarantees that the exact same imputing and encoding happens during training and prediction. The next step is to fit the pipeline and evaluate on the holdout set. First, we'll train the entire pipeline on the training data. This will train the entire pipeline on the training data. So this runs the imputation, one-hot encoding, and then finally the random forest fit. Our next line here will generate predictions for the unseen test set. The same pre-processing steps are applied automatically before we start predicting. Our accuracy score here is the overall fraction of the correct predictions. And then we'll find precision, recall, and F1. Precision is among the predicted survived, how many actually did survive. The recall is among the actual survivors, how many did we correctly predict. And then F1 is the harmonic mean of precision and recall, and so it balances both. We'll print a compact summary, and then we'll show the confusion matrix. If you don't know, the confusion matrix is a quick visualization to see where errors happen, so meaning false positives and negatives. So we can see that our accuracy is around 74%, precision is around 68%, recall is around 64%, our F1 is around 66%. And we can see the test set within the confusion matrix. Next, we're going to find the impurity-based feature importance. I've written some code here to get the transformed feature names from the pipeline. This is the random forest feature importance table, which in this case is impurity-based. Each number is the fraction of total impurity reduction the forest attributes to that feature. The value is summed to around 1. The higher the number is, the feature was used more and more effectively to split the data across all trees. In this case, we see that fair and age contributed the most to separating the survivors versus the non-survivors. On our Titanic dataset, we can see that fair is a proxy for travel class and cabin, meaning wealth has a higher survival access, and age captures the women and children first effect. Sex female and sex male appear separately because OneHotEncoding created 2 indicator columns. Together, they're very influential, which is consistent with known survival patterns. We also see the p-class, which is around 8%. It still matters, but it matters less than a person's fair, the age, or their sex. And the other columns, they add smaller gains. We see that siblings added smaller gains. We see that the embarking columns didn't really have anything to do with our dataset. The caveat of this is that impurity importance is relative and not causal, and it can spread credit across correlated features, meaning fair and p-class. It also doesn't tell you the direction, so meaning whether higher age helps or hurts. Now let's do some light tuning. We'll focus on knobs that can commonly affect the random forest performance. So that is the n estimators, or the number of trees. The more trees there are, the more stabler up to a point, but it means it's slower. The max depth is the cap tree depth to reduce variance. Min samples leaf is the minimum samples per leaf. Larger is smoother, and there's less overfit. Max features is the number of features considered at each split, and adds randomness to our model. We're going to be using grid search CV to clone our pipeline, try every combination in our parameters grid, perform 5-fold cross-validation on the training set, keep the combo with the best mean CV score, and then we'll score with F1 to balance precision and recall for the survived class. Then we'll extract the best performing pipeline, and let's take a look at the results. Let's take a look at the results. Our best parameters is setting the max depth to 12, the max features stays at square root, the min samples leaf is 1, and around 300 trees will give us the best results. Compared to the accuracy, precision, and recall at F1 from above, we've successfully tuned our model. And that's it. Thanks for watching the video, and I'll see you in the next one.